So one example is that the encryption with the key K of the message is 2 times M. Is this IND-CPA? Does it satisfy this definition? Namely, for all attackers that you can think of, their chance of winning, distinguishing between 2 messages from their ciphertext is no more than half. So, yeah? No? Okay, why? Exactly. So, see, given a ciphertext, the attacker can just divide by 2 and then he knows the message. Okay, so for example, in this challenge point here, he can send the message 0 and the message 5. Okay, and if he gets back 0, then it knows it was M0. If he gets back 10, then it knows it was M1. Okay, so he guesses with a chance of 100%. So these definitions are a bit counterintuitive, and it requires a little bit of chewing on them to understand them. But during this class, and especially during the cryptography module, you'll keep looking at it and understand more and more of what it means. In general, cryptography it's a very different way of thinking. And so just chewing on this over and over again, you'll kind of get that way of thinking. But intuitively, you can start by thinking first, is this encryption something that looks secure? Can I even reverse it? Because if you can reverse it and get the message back, then it has no chance of being secure. Then definitely you'll be able to distinguish in this step. But then even when you can't reverse it, it might still not be secure. So one has to be careful, about partial information which is captured in this game. Okay, so I'm going to take another example. How about the encryption of K and the message is going to be a random number. So I'm going to flip a random bits, and I'm going to output a random number for every single message I'm trying to encrypt. Is this IND-CPA? So, okay, the question was how would you decrypt it? So absolutely, this encryption has a problem. What is that problem? Which property is violated? Correctness, exactly. Absolutely. This definitely doesn't have correctness, so it's not an encryption scheme we want to use, because the moment we encrypt a message, we can't retrieve it. But is it IND-CPA? Can someone raise their hand and say? I hear people, yeah? Yes, it is IND-CPA because, there's no way for an attacker to guess which message was encrypted. Between these 2 messages, the attacker is sending these 2 messages to the challenger, but is getting back a random number. There's no way in the world that he can guess which message was encrypted. So the chance of guessing is exactly a half in this case. So it is IND-CPA. It is secure, but not useful because it doesn't have correctness. Okay, so yes, IND-CPA, but no to correctness. Okay, this is no to IND-CPA. Okay, let's try another one. So I'm going to take the encryption of key and the message, and I'm going to add them up, modulo P, which is a prime number that is public. Everyone knows this prime number. But I'm going to add the message to the secret key. And the question is this IND-CPA? Does this leak any partial information about the message whatsoever? Yeah? Exactly. So let's say that the attacker sends the message 0 here. The attacker sends the message 0 here. He's going to get back K mod P. That's going to be the ciphertext. Great. So now the attacker knows K mod P. All right. Now the attacker will be able to know what the messages are. So he's going to send another message, maybe message 1 or message 2. And then he's going to get back a ciphertext. He's just going to subtract K mod P from it. it's going to get 1 or 2, so it will know which of the 2 messages it was, and hence it will be able to say it was the first or the second with a chance of basically 100%. Okay, so this is also not in CPA. And in general, it's not in CPA because even if you, just to build intuition, if you look at this encryption, well, if the message is 0, you already have the key. That's terrible. I mean, you shouldn't be able to just get the key that easily. Attacker should be able to see a ton of encryptions, and even then not know what the keys are, what the key is. Okay, but this so readily gives away the key for a message of, 0. So this is not in the CPA either. Okay. All right, another example. Encryption of the key and the message equals number 3. Is this in CPA? Yes, it's in CPA. Can someone say why? Yeah? Yeah, exactly. The attacker will only always get 3, and from 3 you have no clue what message was encrypted because the ciphertext carries no information about the message. Okay, so even if he sends 2 different messages here, it always gets back 3, so has no clue which one of them was encrypted. So it will only win with a chance of a half. But again, what property does this encryption scheme have? What property doesn't it have? Correctness, yeah, exactly. So it doesn't have correctness, but it has in CPA. Okay, so you see, it's pretty hard to have something with both correctness and in CPA. In fact, none of these examples has that. And over the next 2 lectures, we will be building an encryption scheme that actually achieves both of those properties, but it's not as simple as me just writing, directly an equation like that.